Okay, this first test, integral test, I could give you the formula right away, but I think it's more instructive if I give you examples before giving you the formula. So let's think about this series 1 plus 1/2 plus 1/3 plus 1/4 and so on and so on. And I want to relate this with the integral of 1 through infinity of 1 over x dx in the following way. First, think about the graph. 1 over x is this graph. And then here's 1 until infinity. So this is the area that's being calculated by this, right? And this integral is ln of x, you plug in infinity and 1, which is ln of infinity minus ln of 1, and ln of 1 is 0, ln of infinity is infinity, so we do know that this area is infinity. Now what you want to do is you want to divide 1 through infinity at integer points and build rectangles according to the left sum. So you remember the Riemann sum, right? The left sum is like your rectangle that you build has the top left corner on the graph. So as you can see, this rectangle has the top left corner on the graph, top left corner, so on and so on. And let's look at the coordinates of this top left corner. If you have 1, because this graph is y equals to 1 over x, when you plug in 1 into here, this will be 1 comma 1. When you plug in 2 in here, this point will be 2 comma 1/2. This point right here will be 3 comma 1/3. This point will be 4 comma 1/4. With this knowledge at hand, let's think about the area of the very first rectangle. Base length is? What's the base length?
1.
1. What's the height?
1.
1. Figure not drawn in scale, so it doesn't look like 1. But these are supposed to be the same, so this area will be 1. Okay, base length is 1. What's the height? 2 comma 1/2, so it's 1 over 2. So 1 over 2 is the area. This will be 1/3, this will be 1/4, 1/5. Now you kind of see where we're going with this, right? So here's the statement. The L sum, the left sum of integral from 1 through infinity of 1 over x dx with delta x equals to 1 is summation of 1 over n from 1 through infinity. It's this sum. Okay. Now since 1 over x is decreasing monotonously, because if it's like going wild, we can't say this, but if it's always decreasing and we're using the left sum, then the left sum is a overestimation or underestimation? Over is an overestimation. So L sum is bigger than or less than this interval. So is this side bigger than this or less than?
Greater.
It's greater than, because it's an overestimation. Well, we know that this is infinity, and we know that this is the sum of 1 over n. So what's this conclusion?
1 over n is equal to infinity.
Yes. So this must mean that the sum of all these 1 over n should be infinity. That's how you prove it.
Oh.
Now, it's still not very convincing, I think. It's like you're adding something that's getting smaller and smaller. So if you're imagining this as like moving right with these step size, you're like taking steps that are smaller and smaller. How can you still manage to get to infinity? It's not very intuitive. So let me show you an alternate proof. So, where should I say this? So let me just write here. Alternate proof. If you have 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9 plus da da da, this is bigger than 1 plus 1/2 plus 1/4 plus 1/4 plus 1/8 plus 1/8 plus 1/8 plus 1/8 plus 1/16 plus 1/16, then this is repeated 8 times, plus 1/32 plus, and so on and so on. Okay. Now, can somebody explain to me why this series written here is less than the sum of 1/n? Why is this less than the top?
You're taking. You're taking longer to get to the.
No, it's just, both are infinite sums, okay? Yeah.
Okay.
Yeah.
But what I mean is like you have 1/4 then plus 1/4.
So what about it?
They're two different series.
They're two different series, but I'm claiming that this is smaller than the other one. Why?
You know, when you're hopping, when hops, and then it hops, and then stays for another one.
Okay.
That's
Well,
what it
you
is.
can talk about the step sizes that way. But directly just looking at these two and comparing, how do you know that this is bigger than this?
You're adding smaller numbers.
You're just adding smaller numbers, right? So right now here, these are the same, but what happens here?
That one's smaller than
1/4 is smaller than 1/3, right? And 1/4 is same as 1/4, but then every time they're different, the thing down here are smaller, right? These two are the same, but then occasionally they match, but then most likely they're different, and every time they're different, the things right here is smaller. But then look at this. What's 1/4 plus 1/4? 2/4, which is 1/2, right? What's 1/8 plus 1/8 plus 1/8 plus 1/8? Again, 1/2. It's 4/8, which is 1/2. 8/16 is 1/2 as well. So what is this series? You're basically adding 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus. What happens if you do that? If you add the half again and again and again, what happens?
It just increases by 0.25.
You get to infinity. Yeah. It just increases without bound. Therefore, since this on the top is bigger than infinity, this must be diverging to infinity as well. Yeah. So that's another proof. Yeah. Okay. All right. Now, let me talk about another example. What if you had summation of 1/n squared? Which is like 1/1 plus 1/2 squared plus 1/3 squared, something like that. This time, since I have 1/something squared, I'm going to think about 1/x squared, and I'll integrate this from 1 through infinity. This time the picture is, it looks similar to the previous one, except that 1/x squared is closer to the x-axis than 1 over x as it passes through 1, right? But it's hard to draw that, so overall the picture is like that. And the area from 1 through infinity is, well, this integrates to negative 1 over x, and you plug in infinity and 1. So you get negative 1 over infinity minus negative 1 over 1. What's 1 over infinity?
0.
0, so you end up with positive 1. So this area here is a finite number. It's positive 1. Supposed to be getting smaller. Okay, then again we use a similar idea, 1 and then 2 and then 3. Divide this into integer parts. And we build rectangles, but this time we're going to use the right sum.
How come we want to use the right sum?
Why do you think so? Yeah?
If it's, if the number is 1,
Mhm.
but when you're adding 1 plus 1 over 4 plus 1 over 9, it's
Mhm.
greater than 1.
It's greater than 1, yeah. So this value will be greater than 1, yes. But it's going to be a finite number. Now, I want to show that this is finite. And by the way, the person who first did this didn't immediately decide to use the right sum or left sum. Like, he would be like looking at this, he doesn't know if it's going to converge or diverge. He's like waiting, like, is it going to converge or diverge? And you just keep thinking, and one day he wakes up and says, okay, I'll just try to see if I can prove it converges. Well, I'll just assume that it converges. If I want to show that it converges, what do I want to do? I want to show that the sum is less than some finite number. Because you don't want it to be infinity, right? See, previously when we were showing that 1 over n diverges, sum of 1 over n diverges, we were trying to use the left sum because that way you can say that the summation is bigger than some infinity. So it must be infinity, right? But here we want to show that it's less than some finite number, so that's why we're using the right sum, because right sum would underestimate. Right? Okay. Except that if you actually write down the value of this rectangle, as you pointed out, it's really not this one. It's a little different. So because we're using the right sum, if you plug in 2 to this graph, y equals to 1 over x squared, what's this coordinate? 2 comma? 1/4, or 1 over 2 squared, right? What's this coordinate? This is 3 comma 1 over 3 squared. This is 4 comma 1 over 4 squared. Okay, so therefore, what's this area? Height is 1 over 2 squared, base length is 1. So this will be 1 over 2 squared. And then 1 over 3 squared, 1 over 4 squared, 1 over 5 squared. So it leaves this, the very first one out, but that's okay. If this much converges to a finite value, then adding a 1 will still be a finite number. Don't you think? Yes?
How can you tell when to use like the left sum and the right sum, and which one's an overestimate and an underestimate?
The answer is you don't. You don't tell, because I'm going to package this so that you don't have to worry about that at all.
Okay, all right.
I have a question.
Yes?
What if you did an over approximation for this? Or you did the over?
If you do the over, you get exactly this series, but all you get is that the entire series is bigger than 1. And saying that the series is bigger than 1 doesn't tell you whether it's a finite number or infinity, because infinity is bigger than 1. So you can't show anything. Okay? All right, so now here comes the argument. Summation, this time I'm just going to start from 2 to infinity, right? Because it's from 2, of 1 over n squared is bigger than 1 or less than 1?
It's less than 1.
Less than 1, because it's an underestimate, right? And therefore, this converges. So the idea is this, like you start from 1 over 4, and you add a little bit more, 1/9, and you add a little bit more, 1/6. So it increases, goes up and up, but there's an upper bound, which is 1. The things that you add up can never be beyond this upper bound. So if you have an increasing sequence of numbers, and it can't go beyond certain numbers, then it must stop somewhere, right? So therefore, it must converge. So that's what this argument is. Okay. So that's it. We know that that converges because of this argument. Okay. So I know that you guys are worried about how you can figure out whether to use the left sum or right sum or anything else. But at the end of the day, somebody figured this out for you, and then you don't even have to mention anything. It's a theorem where now you can just say, in the name of the integral test. So here's the integral test. If f of x is monotonously decreasing function, positive function, then the convergence or the divergence of summation of f of n is determined by integral 1 through infinity of f of x dx.
So would that not work with like cosine and tan and all that? Those
Yeah, so sine and cosines, they'll like fluctuate, so you can't use them there. That's why I like ones with sine and cosines.
So then when it would be, it'd be kind of important to know the graphs then, right?
Yeah, so we only use the integral test on simpler things. And then when it gets more complicated, we use other tests. There are like four other ones that's about to come. Okay.
Cool.
Yeah, a lot of stuff. Right. Okay. So it's like this. If we wanted to know that summation of 1 over n cubed from n from 1 through infinity converges or diverges, then you don't have to talk about graphs or like left sum or right sum or any inequality. All you have to say is just replace n by x. You integrate from 1 through infinity. And now the integral of this is negative 1 over x squared, and you plug in infinity and then 1, which is negative 1 over infinity squared minus negative 1 over 1 squared, which is just 1. And then, oh, sorry, this should be a 2. So it must be 1/2. And that's it. That says what?
Converge.
So summation of n from 1 through infinity of 1 over n cubed converges by the integral test. Yeah, that's the beauty of mathematical theorems. They prove something ahead for you so that once you say the magic word, right, then it works. You don't have to say anything else. You don't have to talk about left sum, right sum. That's under the hood. The person who did the proof of this worked it out so that anytime this converges, it converges. Anytime this diverges, it must diverge. That's how this is done. Okay. That's integral test.